Okay, so today we are going to discuss various types of electron microscopes and fundamentals of electron matter interactions. So broadly, electron microscopes can be divided in two types. There are many subtypes, but we'll discuss that in the next class. Probably today, we'll see how we proceed. So transmission electron microscope and scanning electron microscope, right? So last time we briefly discussed about these questions, and the learning of electron microscopy uh, basically revolves around these two fundamental questions. So if you understand these things, so it is much easier for you to analyze your samples. Okay? There is no shortcut, unfortunately. The first question is how do electrons talk to your samples? When and why does an electron scatter? How do we learn from electron diffraction and scattering about our specimen? So last time we discussed about elastic scattering and inelastic scattering. Elastic scattering basically when there is no energy loss, right? There is no energy transfer. So the particle interacts with the specimen with some energy, and it exits the sample with the same energy. So there is no energy exchange. And if there is any energy exchange, energy gain or energy loss, so we call it inelastic scattering. In principle, there is no interaction which is purely elastic that we will discuss later on. But in the layman term, we can say that we can classify uh, uh, in this way. Um, so as we discussed last time that every radiation, whether it is electron wave or photons, they uh, get scattered because of some non-uniformity in the uh, medium. For example, light wave get scattered when there is a non-uniformity in the refractive index. For example, if you take a piece of silicon and right, and there is a silicon oxide on top of that, silicon oxide, and suppose the light rays, this is normal to the plane, and so when the light beam falls onto the specimen, a part of it will get reflected, right, in the same medium, because you are entering from air to silicon oxide, so there is a change in the refractive index, right? So similarly, when part of this will enter inside, will get refracted, and then again part of this will get reflected when it encounters silicon oxide, which is another material. And same process will be repeated here again, because from silicon oxide the wave exits to the air again, right? So there is a change in the refractive index. A refractive index, you can loosely say that there is a change in the dielectric constant. Okay, so uh, similarly, as I mentioned, that X-rays scatter when there is a change in the electron density uh, in the material. For example, you take a lattice. These are the atoms. Suppose this is a two-dimensional lattice, and when the X-rays, so there is a particular electron density. Suppose there is a bonding in this lattice, right? So when we say the bonding, for example, these are all gold atoms, right? So there is bonding. So the bonding, there is metallic bonding, and metallic bonding will result to some electron cloud densities, particularly centered in some way, basically, right? Right. Suppose this is ionic lattice, so then you know that, uh, for example, NaCl, so electron density will be higher around chloride ion than the sodium ion. Similarly, you can discuss about covalent uh, you know, lattices like silicon or gallium arsenide, um, or your graphene, or so there is a particular electron density map around that. So X-rays basically look at the electron density distribution. It does not know that that is your atom. You are calling that as an atom. Similarly, here also, uh, same thing applies. So this incoming optical wave does not know that it is air or it is silicon or silicon oxide. What it notices is the there is some change in the refractive index. For example, you're blindfolded and you are walking on a beach, right? And then you're walking on a pavement along the beach. There is a cafe and there is a paved road, so you can walk easily there. When you leave the pavement, or paved road, whatever it is, and start walking on the sand, then your speed will be lowered, and you can feel, even if you're blindfolded, you can feel that you're walking on sand. And suddenly, when you go closer to the sea, and when your feet experiences the wet sand and the water, then you can notice that there is a change in the environment. So the waves see similarly the change in the surrounding environment actually. And then we observe this change. We detect the behavior of uh, the signal actually through the several detectors, and then we get the information about that specimen. Here, our objective is to know about the sample, that this is unknown, and here we want to know about the properties of the specimen. So uh, once we probe these waves after this interaction has happened, then we know that what kind of interaction has happened, and we can learn a lot about sample. Same thing is in the electron waves or X-rays, whatever it is. So this is the basic principle of all analytical techniques. I think all of you are aware of that. So as we discussed last time, that X-rays are sensitive to the electron density inhomogeneity. Uh, right? X-rays do not interact with the nucleus, and electrons, we look at the overall Coulombian potential, which is coming from electrons or nucleus. So basically, we are looking towards electron-electron interaction and electron-nucleus interaction. Okay. Now, if we look at different possibilities, you can see that you can look at this is your nucleus, and we look at incident electrons. This is the case number one. If you follow this line, so you can see that this is going slightly closer to the nucleus, and because it is getting pulled by the nucleus, this electron, so it is pulled by the Coulombian attraction. So that's the reason that it changes its path. And you can see that this is elastic interaction. So you can see that it just ends up here. So you can put your detector and look at whether there is any change in the energy, at what angle this scattering has taken place. So there are these two information, the angle of scattering. Otherwise, this would have gone straight. So it has deviated by this angle theta, and you have to see whether there is any change in the energy. These are the two informations which you can get. Let's look at the second electron. It starts um, moving towards the nucleus, and it goes fairly close to the a nucleus, and you can see that there is an emission of uh, photon here, and you can see that this electron loses energy, and then it really bends at a very high, uh, very large angle. Especially if you follow electron number 4, so it knocks off, it uh, gives it give the part of the energy to knock off the core electron from the K shell. See that, right? So remember that the energy of the electrons is which you are using is around 100 kilo electron volt, or 200 kilo electron volt, or 300 kilo electron volt. Roughly, it is, which is a lot of energy. I mean, if you notice, uh, it is a fraction of the energy which is required for the core electrons. So core electron energy is around uh, somewhere around 100 electron volt to around 1000 electron volt, right? Or 1 kilo electron volt. Depends upon different kinds of uh, core electrons and elements. But you can look at this data, but it is of the order of like 2 kilo electron volt. It can be your, okay, roughly of the. So if you compare it with the incoming energy, 100 kilo electron volt. So and the energy loss, energy required to knock off this core atom is roughly 1% of the total energy of the incident electrons. You can see that it. So incident electron in electron microscopy needs to just give a fraction of its energy, less than 1% of the energy, to knock off this K shell electron. And so what happens that now from L shell, this electron can jump back, and then you have this emission of X-rays, right? And then these X-rays can be absorbed internally, and then there is a possibility of uh, that can be absorbed by knocking off another electron. Then you have this Auger emission, right? So you can get a lot of information about chemistry of the sample. If you depend, it depends upon what kind of signal your detector is interested in. So entire course is revolved around uh, these few signals. Will be coming back and forth to this kind of discussion, right? So these signals are summarized in this very important schematic. Uh, so I was discussing in the previous lecture also. Let us revise some of these signals. So you have this high uh, electron volt incident electron beam, and what can happen that so this beam can also remove some electron from valence band, actually, uh, which does not in fact require a lot of energy. uh, so then those electrons are called you know secondary electrons. So secondary electrons are useful in uh, SEM, scanning electron microscopes, microscopy. Okay, so if you use secondary electron, uh, uh, secondary electrons, and make image out of that, so you get beautiful topography image, like real life image. We'll discuss it in a special class where we'll be learning only about SEM. Probably it will take 1 or 2 classes because it's a very important technique. So this is elastic process. Please remember that we'll go into detail about secondary electron emission in that class. So I'm not going to discuss it here. So if you do not understand this, do not worry at all. Any of all these things will be repeated several times. So do not worry at all. And I know that many of you may not be able to understand today, but do not worry. So X-ray emission we have already understood. Visible light, normally we do not care that much, apart from unless you are a hardcore physicist or metallurgical engineer. Um, then brimstone we do not really bother that much. Inelastically scattered electrons we learn today a little bit. It is very important for chemistry students. Um, Elastically scattered electrons are there are 2-3 types of electrons. We'll learn today as well as in the following lecture. This is very important signal. This is very important signal for us. And Ajay, we learn backscattered. Some of you are already familiar. Backscattered uh, electrons, backscattered signal got uh, famous because of Rutherford, uh, Rutherford's experiment. In fact, it was done by Rutherford's students. I'll tell you a story later on. The Rutherford did not believe. It seems that it can happen, but the plum pudding model of J.J. Thomson, and so Rutherford in the Rutherford lab, they bombarded um, alpha particles, okay, which are nothing but helium atoms, and you strip off 2 electrons from helium, then those are the uh, nuclei of helium, and you bombard those positively charged particles towards a gold foil or whatever sample you take, and many of those alpha particles uh, uh, were scattered in the same direction, almost 180 degree almost. So that was surprising. That means uh, there is a positive charge which is uh, centered in the in this inside the atom. So that is causing strong Coulombian repulsion. So then the model was, I think all of you know that it was changed. So how do you do it in an instrument? So you have, you can see that this is so just a moment. So you can see that if you, I don't know how to zoom it. I have to learn it. I think I saw one postdoc who was presenting and he was zooming it. Let's see if I can zoom it. Yeah, I called the student. So anyway, so I'll learn it later on. Uh, that will be easy. So you can see that sample needs to be quite thin. So it is written here thin slice. So you have unscattered electrons. So these are actually, you can see that these are considered as transmitted electrons. Transmitted electrons are inelastically scattered electrons, unscattered electron, and elastically. These are 3 categories. We'll learn how to use them. Um, so you can use them in the image mode. So you can form electron microscopy image, or you can use it in the diffraction mode. You get the diffraction pattern. So then you get a lot of information about structure, crystallography, etc., etc. You can do chemical analysis, yields, etc. We'll learn. The next important slide is on your screen. Please pay a lot of attention to this. If you miss anything, you can ask me, but you must learn it at this moment. What you see is, see, the question arises that uh, what is the volume of interaction of volume of, like, sampling volume? Like, suppose you take certain thick sample. So how deep? I mean, how many atomic layer or I mean, you are picking up the signal, and so the question always comes that what is the lateral sampling size and depth wise. Okay. And this is the case when so there are two ways you can do the electron microscopy. In one way, you take parallel beam of electrons. So obviously, when you take the parallel beam of electron, so your sampling area is larger than you take a nano probe. So in this case, electron beam is uh, focused, few angstrom. So so even if it is focused on few angstrom, so these electrons will uh, travel inside, okay, and then there will be a lot of scattering events, right? The photons will travel and stuff like that. So here, if you see that, if you notice something here, so this is 1 nanometer, 5 to 50 nanometer, 100 to 200 nanometer, and then bulk. You can see that uh, here most of the signals which involve a detection of electrons will be sampling. The sampling depth for those signals will be fairly less, only few nanometer. But if the signals are photons like X-rays, so then your sampling depth is much larger. So because photons do not interact that strongly with the sample, so they can penetrate deeper. And even if the photon is, suppose your detector is somewhere here, so suppose photons start traveling from here, it will be able to escape the sample. Okay, but if electrons start traveling from here, it will not be able to reach to the it will not be able to exit this sample safely, because it will be absorbed by a neighboring atom within the sample. Only from the top layer, from few nanometer, these electrons will be able to escape from the sample and will be detected. So that's why, so thumb rule is that the techniques which involves detection of electrons, the sampling depth will be far less, and the techniques which involve detection of photons, the sampling depth will be much deeper. And implications are not just in the electron microscopy, implications are around you everywhere. Look at the Raman spectroscopy. So Raman spectroscopy, you are using a laser beam, which is again electromagnetic radiation, photon of typically either it is UV or visible or near IR or sometime IR. Normally, those lines are fixed. Okay, so the sampling volume, because you are in Raman, you are showering photons, and you are detecting also photons, right? So photons do not interact that strongly, so they will be able to penetrate deeper slightly. It depends upon, again, I mean, there is no. It depends upon the wavelength of laser also. For example, and also the sample type. I'll explain it in ellipsometry lecture. So but X-rays, for example, X-ray diffraction sampling depth is fairly large. So that is the reason that you need to take fairly thick sample. Otherwise, you start collecting the signal from the substrate. So suppose you are doing X-ray diffraction, so you need to really, so sampling depth is fairly large in X-ray diffraction. X-ray being again photons. Okay, so this is the thumb rule. X-ray photoelectron spectroscopy, where you are bombarding X-rays, but you're detecting. Please remember, you're detecting not X-rays, but you're detecting photoelectrons. So then the sampling depth will be few nanometers only. Please remember. Okay, so please remember the tech. For example, UV visible absorption spectroscopy, sampling volume. I'm talking about solid samples here. Of course, liquid sample, there is a different ball game, because density is far less for liquids in comparison to solids. So then basically you can afford to put path length is quite large, but then it depends upon the concentration and then interaction uh, uh, of that that photon at that particular wavelength, whether it is interacting, whether it is getting absorbed by the something in the sample. So those are the special cases, but generally speaking, so you can see your mobile signal, which are again electromagnetic waves, the radio waves, those are all able to reach, penetrate the concretes, glasses, and your pocket, the clothes. They're able to, your bag, they're able to reach well within the objects where you are trying to get the signal. And the towers, mobile towers, are really far away. So you can see those waves are getting multiple times scattered. Those are gigahertz range, right? Um, for example, it depends upon whether you are using 2G, 3G, 4G, or 5G. So there you are uh, changing the frequency, right? So so when you use so then that's the reason that for 2G you need towers really far away, because those are longer wavelength actually. So they do not get scattered, they can travel really far away. So so shorter waves get reflected, get absorbed. So that's why 5G needs booster antennas at a closer distance than 4G. Then 4G in comparison to 3G, 3G comparison to 2G. That's why if you go to Himalaya and other places, you still find 2G is preferred there for voice communication. Okay, so so you can see that in this, it's all described here that Auger, uh, Auger or XPS, they are around 1 nanometer. Secondary electrons can be picked up around 100 nanometer. Then you can see that X-rays go to 10, so much deeper actually, tens of microns actually. This is very important, and this generates lots of interview questions. Please remember this. This is a very important slide. That's why I spent a lot of time here. Many times students forget this. And okay, so let us move. So Bremsstrahlung is not very important, so we can skip it. Yeah. So yields is quite important, and I'll not be teaching. I'll be giving you idea about yields, but I'll not be going. There is no dedicated lecture on yields unless you require that, because this technique is quite special, and it is not available. Yields detector is fairly expensive, fairly sophisticated, and it is not available at NCL. But if you like to do these, I think it is available at IIT Mumbai and other places like Saha Institute of Nuclear Physics and some of the other labs. Uh, you have to check the availability. And so yields basically. So when the electrons, they lose some energy into the into formation of plasmons actually. Okay, very subtle amount of energy, few electron volts. So those electrons, are detected in the yield system. So this is the yield system. So this is, you can see that this is like another microscope. So this is fairly expensive. You have the electron source here. You have condenser, series of condenser lenses. Then you have objective lenses. Here you put the EM sample, and then you can get all sorts of signals. I believe you can at your end you can zoom those things, so you can pick up Auger signals. Uh, here you get the X-rays, so you can get the energy dispersive spectroscopy, X-ray spectroscopy, right? Uh, and then you can uh, uh, you can basically collect these primary electrons will undergo subtle energy loss, and the energy loss is that if you can calculate that, so then you get a lot of information about atomic composition, chemical bonding, valence and conduction band electronic properties, surface properties, and many things actually. So yields tend to work best at a relatively low atomic number, which is also an advantage because not many techniques work best for those uh, 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 elements in the periodic table. So you can see that this is electron energy loss, and you can notice that it is an electron volt. As I mentioned, that the energy loss is very less, and you can see that this is a plasmon resonance. So here I would like to add you that add here that most of the when electron enters your sample, so most of the losses happen because of the plasmon resonance. Plasmon resonance processes. We'll discuss it later on, and this is also an advantage in making some advanced techniques like these. So if you can detect those uh, signals, so you get a lot of information. So you can see that this is the zero loss peak. So you get most of the electrons which undergo no loss. So basically they there is no loss. So a lot of electrons there most of electron undergo. So it's a fairly large peak. So if you zoom this area, you can see that. So you get this atomic core loss peak. So it's similar to what information you get in XPS, but you get fine structure also if you zoom this. So this tells you about lot about chemical bonding and other things. And you can see it is similar to if people who have some idea about X-ray photoelectron spectroscopy, you can see that you get this core level peaks. For example, iron K alpha, iron K beta, silicon K alpha. So so this is kilo electron volt. I was we have discussed. So yields is often as poor. Yields is basically complementary to a very poor uh, 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 a poor man's technique, which is called EDAX. EDAX is a poor man's technique, and EALS is basically rich man's technique. EDAX is better in quick identification of atomic composition. And believe me, NCL students and many at many places, students do a lot of mistakes when uh, they analyze the EDAX data. So basically, EDAX can tell you how many atoms are there of a particular type. So suppose uh, you have iron oxide and aluminum oxide. So then you get to know about iron and aluminum and oxygen. You dare not to uh, um, know, because that's not possible. But many people try to do that. But there is there is a lot of error in EDAX in the atomic percentage. But we'll discuss about that. That people show all kinds of funny data without knowing the limitations of the instrument. So please do not do this mistake. We'll spend some time later on. It's an advanced topic, but I'm telling you that the practical implications which you see day in day out, that students do a lot of mistakes in EDAX analysis. Might see in the poster presentation and science day, a lot of those problems. So, but EDAX excels as it's a very easy technique, and it can tell you in one shot what kind of atoms are present, what kind of elements are present. But it will not be able. It will give you a rough idea. It will not be It will not be able to uh, confirm your stoichiometry precisely, especially for lower atomic number. So the problem lies here that EDAX, the energy resolution is very bad, actually tens of electron volt. yields as well. So when the energy resolution is so bad, few tenths of electron volt. So suppose there are two close by peaks uh, uh, which are not basically spaced. So it can miscalculate actually a lot of things. So application of yields are many, but I'll give you example of carbon, and everybody knows this uh, typical peak of carbon. This one, this is very famous, 284, which is prominent here. But you can see that uh, uh, in 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 XPS you can see a lot of subtle information, but you can see that for graphite, fullerene carbon 60, and diamond, you get a lot of difference in the fine structures. Actually, this is lots energy. So because of the bonding and the surrounding environment, diamond obviously the bonding is very different, and graphite in comparison to graphite. But graphite and C60, I mean, they are derived from graphene. So when you stack graphene one over another, then you get graphite. Of course, there is a pi bonding, and there is a stacking one-to-one interaction and all kinds of stuff. C60, it is not there, depending upon what kind of buckyball you have. So there is a change, but uh, EDAX will never be, EDAX does not have that kind of energy resolution. If you are very careful with the XPS, you can get, but most of the time signal is too noisy. Um, and, uh, and the fitting also is, fitting require a lot of skill. So many times students do not fit properly, and they make ant look like elephant and elephant look like a goat, or something, rabbit or something like that. So so many of these techniques depend upon deconvolution of data. So, for example, there may be multiple peaks here. This peaks looks very broad. So you may need to uh, deconvolute this large peak into two peaks actually. So same problem is in the Raman, and almost everywhere, be it UV visible absorption spectroscopy or photoluminescence, or X-ray diffraction. So peaks, EDAX. So the signals are sometimes spaced too close to each other to resolve. So you need really a skill to you know, know what exactly it is. Otherwise, you can make wrong conclusions, funny conclusions. So this is very interesting slide, which I like. This is the data on. This is elemental. I think all the chemistry students will love this slide because there is a lot of detail here. It talks about uh, elemental distribution in uh, Okay. It talks about elemental distribution in a sample of lead chromate PbCrO4, and covered with silicon oxide of about 50 nanometer, 50 nanometer thickness. And you can see this is the image taken by uh, uh, basically elastically scattered electrodes. So you see topography usually, but you can see actually the core shell structure because of the variation in the thickness and material Z. You can see here the yellow you know shell, because silicon electron Z is different than PB and CR, which are more towards the core. But if you look at the silicon peak E signal, you can see that shell is lighting up, and there is some mixing. You can see in the at the interface also. You can see that there is some signal at the interface. So some silicon has entered. Uh, no, it's not actually uh, the I mean, it's from the top because it shows the top layer also, right? You understand, because it's a two-dimensional projection of three-dimensional objects. So what you see silicon dot 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 here in the middle yellow one is actually from the top and bottom layer actually, right? So oxygen you can get 532 electron volt, and then you can see chromium L shell excitation. If you catch the electrons, if you catch the electron with the loss of, this is the loss, okay, electrons have undergone this loss. And believe me, if you try to look at 300 kilo electron volt, uh, from 300 kilo electron volt, which are majority of the electron, and 300 uh, 000 minus 580, how much it will be? It will be, fairly, very small, very not very different from this number. I may not be able to calculate immediately, but you can do this calculation, and something of that order. Uh, okay, so this is not very far from this peak. So this peak is not very far. So it requires a monochromator um, and other things to. Uh, so it becomes an expensive. So next technique is uh, based on electron diffraction, and uh, which is called high resolution TEF. So there you can start seeing, you can see that you can start seeing, you saw it in the that movie, that you can see the lattice lines, the arrangement of atoms. So here you can see that these are the planes of atoms, and so here electron beam, if you notice, uh, unlike in X-ray diffraction where the angle is too large, here electron is traveling almost parallel. So you can see that theta is very small. So electron is traveling almost parallel to the atomic planes, which may surprise you, um, uh, or some people may not be surprised. This reason is that if you solve this equation, so d is the same for, I mean, if you take its interplanar distance for a particular lattice. So for example, you take d as one um, angstrom or whatever, nanometer, whatever you, for simplicity you can put any number. So lambda is in lambda is very small. I mean, please remember 2.7 picometer. So theta, this angle will be a small fraction of 1 degree. So that's the reason that these electron diffraction happens at a very small angle. So uh, it is not like, so there is a difference with X-ray diffraction. In X-ray diffraction, you need to, if you are familiar with X-ray diffraction, powder X-ray diffraction in as a special case. So there you need to scan the 2 theta from in a large angle, range from 10 to whatever 70, 80 degree, 90 degree, whatever is available. So then you get some peaks. But here, if you see that in one shot you get this diffraction spot. So this is center one. This is center spot 000 diffracted, and then you can calculate the d values by looking at the distance from the center spot to the other spots. And so this is basically a zone axis. So you can see this is an niobium aluminum. This is an alloy, niobium aluminum alloy, and you can see that beautiful. This is called electron diffraction. Okay, this is electron diffraction, and this electron diffraction you can generate when you allow the parallel beam and diffracted beam both to merge. And okay, we'll discuss it later on. So the next topic is Kikuchi lines. Kikuchi lines are very, very useful. You can see day in, day out in your samples, especially if the sample are thick. So when you take your, when you synthesize some particles and you make your sample and inside and bombard electron, high energy electrons. So you may see in the diffraction, so you may see these kind of lines. You can see these lines actually. You can see this one is bright line, another is there is a pair of two lines actually. This is explained here. So one is deficient line, one is a bright line. So these lines are very special actually. Those are those will learn later on. But this is what an electron microscopy can do for you. Another very important technique is EBSD, which is primarily used in SEM. So which all can also give you electron diffraction for thick samples. Okay. So now let us look at different parts of an electron microscope. So primarily you can divide it in four parts. One is electron optical column, which is most important, most expensive part. A vacuum system, which because you need to have vacuum inside the uh, column. Why do you need vacuum inside an electron microscope? Why you can't do electron microscopy in air? Somebody will reply to me. Somebody would like to unmute and respond.
There may be ionization and scattering of electrons.
Sorry, can you speak loudly?
Hello, sir. There may
Yes,
be
can you speak
ionization
loudly?
of gas inside the
Yes,
chamber.
yes, you're right. You're right. So the air molecules can get ionized when you bombard them by okay by radiation. Um, okay, Manisha, can you check the snapshot of participants and send me the snapshot? Okay.
Okay, sir, I'll send
Yeah,
you.
you can keep on taking 2-3 times at the end of the uh, presentation as well as in the beginning. So I have some record, and you can send me for each lecture, uh, and you those images you can put uh, maybe date. You can change the name of the file by the date, okay, of the lecture. So
Okay,
I
sir.
put it somewhere. So
Okay.
yeah. So then you need electronics and then control software, obviously. So now we can discuss the analogy between a slide projector. I don't know whether you have seen the slide projector. My PhD defense, for example, was on a slide projector. Now, but you can see the modern version of old-fashioned slide projectors, which are connected with the laptop or a desktop. But in my PhD defense, we used to have uh, a light source, fairly bright light source, and then lenses, and then we used to put our slide here, transparency. And you can see those things in the old-fashioned cinema halls, similar thing. But only thing is that it rotates very fast around few, like some frame per second, faster than human eye can detect, so that human eye detect uh, that as a movie rather than collection of several frames, right? Movie is nothing but collection of several frames. So for example, 30 frame per second or 60 frame per second. Nowadays people are talking about 120 frames per second, but it takes huge amount of data. uh, so you can see that this is the object here. This is the object here. Slide is an object. So when you so slide, some part of the slide has some font written on that, right? For example, A, V. So when you are falling, then the light is falling. So those areas of A will block the light, like B, and other areas where the font is not there, where you have not written something, will allow the light. So you will see a large A here. So electron microscopy is transmission electron microscopy. In but transmission electron microscopy is exactly the same, exactly the same. Instead of the light source, you have the electron source, right? So that's why you call it the transmission electron microscopy. Got it? So you have a condenser set of condenser lens, and you have objective lens. So you have your specimen here, and then you have set of apertures, and then you form. So you can select the here. You can, so for example, you have a entire paragraph written on this on the slide, and for example, there are 300 words. So you can select which word you want to magnify. So in TEM, the sampling size is quite an advantage. So you can select a very small area, and you can do analytical chemistry from the area which you want actually. So unlike otherwise, if you compare with XRF or ICP, though they are quite um, accurate, but stoichiometry or some other information, if you want to take, you collect you on from the entire sample, which is quite large. Same problem for powder X-ray diffraction. So whatever information you get is from a very large uh, collection of crystallites. Here you can pick up a tiny single crystal because if you have millions of single crystal, that becomes a powder actually, right? So, but in fact, you can do single crystal X-ray diffraction even when your particle size is very small. So another analogy, you can see that this is how different components are there. It's a repetition, uh, and you will notice this repetition uh, again and again. You will notice. So it's an advantage of this course that most of the slides are getting repeated. Okay, so if you miss something, then uh, you know it is coming in another lecture. So you can see that there is this is first condenser lens C1, second condenser lens C2. So these two condenser lens basically helps uh, to basically to shape the electrons. Suppose you want parallel or you want them pointed. Um, okay, so you can select the settings of these lenses, and these are just magnetic coils. These lenses are actually uh, uh, copper coils which are cooled uh, at certain uh, temperature. So there is a cold water through chillers which flows through these copper coils, because any uh, change in the temperature even by a few degree can change the magnetic field. And please remember that lens, please remember the Coca-Cola bottle, glass bottle bottom. So remember the spherical aberration, remember chromatic aberration, remember Rayleigh criteria. Rayleigh criteria allows you to resolve the uh, atoms by 2.7 picometer, but the lenses, imperfect lenses, do not allow you. And so this is the problem with imperfection in this area is the problem. And there's a lot of research which was especially these lenses, because they are closer to the sample. So after that, then these are the projector lenses. You keep on this is for magnification. Okay, this area you keep on magnify. And here I will show you movie on a very beautiful movie uh, on Monday. And okay, probably, yeah. So so you can form an image here. This is the viewing screen. You can see from here. You can put your eye here, and you can take a photograph. Um, um, okay. I will show you when I started my um, uh, work. First time when I used electron microscope, we did not have the CCD camera. CCD camera came very late actually. So we used to take TM images on normal photographic film, and I still have a lot of these uh, objects good for a museum. But in offline class, I used to teach in detail. A lot of these objects I will take from my drawers, and I used to show all those things. But here it is not possible in online classes, and so I'm sorry for that. Um, but yesterday, last time I was talking to the previous batch of students who have attended my offline classes. So my obviously my Blackboard teaching is entirely different. Uh, and in online teaching, uh, there are a lot of limitations. So you and I both are working with those limitations. But believe me, the in real class is very different. Actually, I'm on the blackboard, and students are on the board, and we are all jumping around, and we are discussing, debating, and it's a different thing actually. So anyway, we are learning something at least. So this is you can see that from uh, electron. In fact, I have electron source filament in my drawer, but maybe next time I will show you. Today I have not started my video because I'm using the pen on the screen, so it's not very convenient for me to. So you can see that these are gold nano plates, and these are synthesized by antibiotic molecules, cephalexin, which is beta-lactam antibiotics, very weak reducing agent. And here you take gold salt, HAuCl4. So Au gold is in 3 plus oxygen state, and then you have H plus, and then you have 4 chlorides, right? So you take these beta-lactam antibiotics. So this antibiotic acts as a very weak reducing agent as well as a capping agent. So it gives 3 electrons to this gold. So this gold 3 plus get converted into Au0, right? And so if you take axial diffraction of these plate plates, so you get this is 2 theta, and this is intensity. So you get very sharp peak around 111 direction. So and you can get beautiful images out of these samples. And this is part of my first PhD student, uh, Dr. Rabia Jagannathan. So I put this image long back when I started teaching to NCL students, probably 2006 was my first class, 2007 perhaps, first course which I gave to students. So some images are very historical. So this image was produced way back in 2006. Okay, and you can see it is still beautiful. If you zoom it, you will find these are contours. There are some contours actually. If you find these are, you find these are there are some contours, right? You can see there are some contours also. Why these contours are there? You can see that you can learn a lot. You can see that here you see on these thinner gold plates, you can see structures. I'll erase it again. So here you can see on these particles, large particle, you can see uh, some structures. But if you notice, there are thicker particles also. Where you do not see any structure. So if you compare between this and this, so this is an example where electrons are uh, coming on to this sample, right? This is a sample, and electrons are being blocked. So this is thick enough. This particle is thick enough that electrons are not uh, coming out that much, right? So the thickness is thickness contrast. It's called thickness contrast. So you can see that electrons are mostly blocked. So that's why it is quite dark. Okay, and if you see that this is grayish, this is grayish. So you can see that here electrons, so suppose thousands electrons are coming. Okay, so here, so some of them are coming outside. That's the reason those electrons are actually uh, carrying the information about these contours. But here you do not get any information. Here you do not get any information about internal structure. Obviously this is useful because you can put a cursor and you can calculate the size and shape. You can see the shape of these darker objects. You can, so it's useful. So these things are useful, right? To calculate, you can see that these are faceted structure. These are hexagons. You can see this one is hexagon, right? Most of them are hexagons actually. They are. This is also hexagon. This is, you can see this is a truncation. There is a truncation, truncated triangle actually, right? There is a truncation. So this is related to the uh, so this truncation happens because of surface energy minimization. And there is also role of chloride ions. I teach it in a separate course, which I think I taught 2 classes, and you can find it's that course is hardcore chemistry. And um, how the how you control the synthesis of inorganic matter. And those 2 lectures, at students request, I have left on the YouTube. So you can, I think those people are watching on those things. So because those lectures you do not really find, so there are 3 4 more lectures due in that series, in the synthesis of materials, chemistry of materials, uh, where you learn a lot of secrets, how you can control the shape of these things. So here fluorides play a major role, which influences the uh, formation of anisotropic particles actually, right? So gold is shape is supposed to be cubic or truncated cubic, but why is it making two-dimensional structures? So this we found when we started increasing the concentration of chloric acid. So more chloride ions in the solution, we started getting more of these structures. So, so another category is environmental transmission electron microscopy. This is very popular uh, among students from catalysis, because they see, the problem with conventional TEM is that you can, with conventional TEM, which is available right now at NCL and most institutes, is that uh, when your reaction is done, so you take your material and disperse it on TEM grids. Okay, in the powder, basically they are dried uh, powders actually. You can put them in some solvent, some suspension, some solvent, and then, but eventually you have to dry the particles out. I think I explained that in the movie. So so that is the end result when the story is over. Okay, entire um, so if you want to see the live formation of the particle, the intermediate steps, so normally students, what they do, they take samples from a reaction which is continuing. So they take some samples and then they make TM samples out of that, and then they uh, solve this mystery, how the matter is forming, what are the intermediate phases. But but sometimes you are not interested in that. You want to see at high temperature and high pressure. You don't want to break the uh, reaction environment is so special that you it does not allow you to break the pressure and play with the temperature and some gaseous environment is there. So nowadays the sample holders are very special that you can do all that thing. So um, so there are so many examples, and I organized one one lecture from a company. So they sell special type of TM sample holders. So there you can mount the sample, um, okay, and then it allows you to control the temperature and pressure and other you can. Okay, so there are several innovations happening recently into transmission electron microscopy from the sample image sample environment side, not just the lenses side. Okay, lenses side is a different thing, but at the so you can read this slide. It's a busy slide, so I will not. Okay, so different kinds of, now if we are coming to the end of this presentation. So know your instrument before using it. Most of the time, students do not note down the details about instrument. When I say instrument, instrument is not something like your motorbike that it has certain cc engine and it can run at certain speed and it's a certain, it has, that is very very simple. But one TM is basically a modular system. In TM, you buy uh, the imaging system plus the uh, the effort lies in knowing the type of detectors. Add-on detectors are uh, very special. So not only you need to know what kind of lenses are being used, because that will decide the resolution. Okay, what is uh, you know uh, the spherical aberration coefficient and CC. So those things come with the manufacturer, and manufacturer will tell you what is possible and what is not possible. But there are detectors like, you have the secondary electron detector, you have EDEX detector, you have other detector. So they have different capabilities. So it is very important to know. And also you can have different kinds of electron sources. So for example, thermionic source or field emission source, and they are entirely different, completely different. If you take the same image using thermionic gun, where electrons are being pulled from the filament by heating it to high temperature, or you are applying electric field to pull the electrons out of the filament, which is usually either lanthanum hexaboride or tungsten. So it is completely different picture, actually completely different results will be there. We'll discuss it later on, but results are very different. So you have to know which source you are using, what is the voltage which you are using. Those details about the instruments, you will notice in the next lectures that if you change from 100 keV to 300 keV, a lot of things happen actually. It's not always that you need I mean, the question arises that which voltage is good for you. We'll discuss it, because without science, you cannot get this answer. But modern instruments, these are all old-fashioned instruments. Actually, these are all phased out. These are old slides. But these instruments, they are just for your basically knowledge. Not necessarily they are available in the market, or I am favoring one company or something like that. Nothing like that. Just to teach you that what is there in a typical electron microscope. So first thing is that the vendor will tell you what kind of field emission gun, whether it's short key, hot short key, cold short key. Okay, so those things we will discuss. What kind of voltages you can apply, whether you can change the voltage, what is the point or lattice resolution. There is a point resolution and there is a lattice resolution, right? You saw that right, those lines in HRT. So you can see that those resolutions are like, this is 2 angstrom, this is 1 angstrom. From where this comes actually, and can you bypass this? We'll see at the end of the course how do you get this resolution, because this resolution is not the same what we got from lambda by 2. This is very different actually, and this is fixed. These numbers are fixed for next comes. This is most important actually. This tells you about this is the property of lenses. Okay, and so this is fixed. You cannot change this. Once you buy the instrument, the operator, and you should put these numbers into the paper when you put the materials and methods. So this should go into your paper, that what is the spherical and chromatic aberration coefficient for the instrument which you are using. And you can tilt the angle of the specimen. You can tilt in different directions, x and y direction. But it is one of the thing is similar to what you do in X-ray diffraction, but you don't need that much of tilt. And then you can have different kinds of functions, basically like CBED, convergent beam electron diffraction, uh, and whether you can converge the beam. We'll discuss this. So this is very popular among chemistry students these days, that because they are want to know from a smaller area. So in contrast to the beam like this parallel beam, if you can converge the beam and converge to 3 angstrom nearly. So this is these are the capabilities. So you need to know what is the capability of the instrument. So this is real instrument. You can see that. And another thing you need to know whether what kind of CCD camera it has, what is the pixel density. I mean, not just you have to know about your own mobile phone which you when you buy, but people are not very careful when they take the image for their PhD degree. But they are very careful about the pixel and all those things when they buy mobile phone. What other things this instrument can do, you should know. So this is a very useful uh, comparison. Again, this is not in the market. This is a very old slide, but it is good for at least you learn something from this. It will be discussing this in many different lectures, but you can see that this is from the manufacturer actually. Okay, brochure. This is from the brochure. I have taken from the brochure of the TM manufacturer. So this is very serious. You can see uh, when you have money and you go for shopping, that I want to buy TEM. That's what you will get. For example, you have uh, different versions of the car, right? One is then they charge you more and more money when you buy different versions of the car. It is same thing. Here you are changing the lens, twin lens, S, S till S twin or ultra twin or super twin, whatever they call it. Like you have this VXI, Ciaz VXI or LXI or what in the car actually, right? Maruti has different series. So you can see that here, if you pay more and more money. So this is basically, if you go into this direction, money, goes by several crore. Okay, believe me, it just increases by several crore rupees. But you can see that there is not much change in the resolution, right? It just goes by a fraction of uh, so. But I have seen that students sometimes they misuse it. They will just uh, put something which is not possible. They will claim resolution which is not possible by these techniques actually. Line resolution is used for HR team, as I mentioned. Point resolution is for normal TEM images, which I just now showed you Ramya's gold nanoparticles. So, okay, information limit we'll understand at the last in the last lecture what is information limit. Uh, okay, uh, extended resolution I will explain everything. All these things I will this magnification range. This is camera length, which basically operator gives you whatever camera length he is working uh, on. Maximum diffraction angle, you can see that it is plus minus 11 degree, which you do not need actually. For bright diffraction happens in fraction of 1 degree. So but you need it for high angle annular diffraction pattern. Okay, so you need this for HADAF actually, STM HADAF. larger angles, but you do not need for routine things. So you can see HRDAF resolution is this one. HRDAF, I will tell you, it is very important, very useful. One of the most useful technique these days. These are the tilt angles and other things. We'll come back to that because you may not be able to understand at this point many of these things. But as I always promise that we'll be coming back to this. So I think so. You can. I will share this slide. These slides are already shared into that Dropbox folder which I have shared with you. Please go through that. There is nothing for me to explain here, so I will skip um, these things. But I think you should look at these funny images. For example, you can see the size of the operator. Okay, he's sitting here, and this is large. Uh, Such large electron microscope. Many times students ask me why limit it to 300 kilo electron volt? Why not in mega electron volt? So you have it here. So it's not much useful, but for some specific purposes, so there are different kinds of TEM, and it's all different kinds of TEM. So I with this I end this lecture.